is blowing in this direction. And that's also interesting because a roof acts like an aircraft wing, like an aircraft wing. Yeah. And how is an aircraft flying? It flies because you have under pressure on the upper side of the wing and you have overpressure on the underside due to the dynamical flow. And this is what happens also if you have the wind blowing. You get under pressure on the roof. So yeah, there has to be very, very strong wind to get a positive pressure on the outside of the roof. Normally it creates negative pressure due to this wing effect. Okay, so now let's look onto how many. It's easy to calculate that. I won't go through these calculations. You have to believe me at that point, but it's easy to do that calculation. You can calculate the amount of air going through here. You can look how many water molecules are in it, how many grams per cubic meter, and then you can calculate how many humidity is transported this way. And then you will end up with 360 grams of water vapor per meter of this per day. Now you remember diffusion, that was 5 grams per square meter, and this is 360. It's almost 100 times the amount of humidity transported by convection. And now this won't work, even with a ventilated roof. It's not working. Yeah? That's too much. Yeah? This amount of extra water vapor transported through the construction, even with a ventilated roof, will be a reason in almost any case for structural damage on that side. I don't think I have a picture in here. In the other presentation yesterday, I had a picture showing this with a modern roof. Yeah, that if it's not airtight, you have this type of. So that is. So that's the most important slide here. That is the reason why in winter cold climates you have to build airtight, right? Because otherwise you almost immediately get these types of water humidity induced structural damage. Okay, so now I mentioned this. We come to that problem of a not ventilated roof. And you sometimes are in a situation where you cannot avoid it. Especially with flat roofs, you are quite often in the situation. Now, you can always avoid it, but it will be much more expensive. Much more expensive. And now, also most of the builders know that there is a possibility even to build these types of constructions. And so they will avoid to have these extra costs to ventilate in such a case. In the case of our construction with the tilted roof, it's not that big a deal. You can always make it in a way that there is a ventilated roof. I just mentioned that. I don't want to be understood in a way that it's not important. It's the best idea to do here. Yeah. So the best idea would be to remove this a little bit, to have a depth of 3 to 5 centimeters of ventilated air, and to have this second layer. It's always what we recommend. But if this is not the case, we are immediately at a completely different situation. Because now, even the water vapor which comes into the construction due to water diffusion cannot be ventilated out on the outside because it's tight there. And of course this layer is cold during winter. So you definitely, from time to time, would get a higher humidity on that layer. Yeah? It's not avoidable. You get that. But the question is, how high would that be? And at the end, of course, during other periods of the year, during the summer, it can evaporate again. Of course, then to the inside. And these things can work. I'll show you, as long as the transport of water diffusion from the inside, or all the water coming from the inside, is really low. Yeah, that's the condition. It has to be really low. So it has to be, of course, very airtight, and it has to be, of course, also reduced in water diffusion. What that means is that you need a diffusion barrier here, something which has a little bit higher resistance due to water diffusion. That is some film materials which are more watertight than other materials normally used at that point. So the diffusion could be managed as long as it is very low. But if we now have an extra transport of air due to convective, due to leakage, due to untight construction, we run into serious problem. This is what is shown in the next slide. It's mainly a calculation of the balance of the water coming in. What always sometimes is confused by people is that they think that if you have an untight situation, if there is air going through, well, that would also help to dry it. And that's not true. This is what's easy to show. It's not true. It's the forces driving the air through the construction. They are especially high during winter, and they are not very high during summer. So what is driving the higher humidity into the construction by convective vapor flow is doing that during the winter when you don't like it to happen, and it's not working during the summer where you would need it for the extra drying. And that means that if the air tightness gets worse and worse, this is what I show here. Yeah? This is a result of 0.4 air changes per hour. I recalculated it to have an easier measure to tell, because you might all know about pressurization results. And we have higher untightness levels, to 2.4. We see the added amount of net convective humidity blown into the construction will rise and rise and rise all the time. And the amount of humidity you can dry out during the summer, of course it will also rise, but also only a little bit. So the last point where the drying capacity is higher than the added humidity is at a level of around 0.4, between 0.4 and 0.6 air changes per hour. So this is why it's especially important in such types of constructions that the construction is really airtight. Otherwise, you will run into these problems. Yeah, so that won't be working. And there are a lot of examples of heavy structural damage of constructions like this. This is why a lot of construction firms don't like to build this type of construction, and it's right. I also do not recommend, but they have to know, if we do it in a really airtight manner, and if you also keep track of the water diffusion, it's possible. It's possible to do, but only under these conditions. So then it has to be especially airtight. Okay, so now this is our construction. I already shown that. Now we installed some measurement devices. Completely agree. These are things. That was the theory. Now let's look into the practice. What's really happening? We installed some humidity and temperature measurements in the insulated construction this way. What you see here is the green roof, is the film for the water stop from the outside. That is the load-carrying timber construction. These are the load-carrying beams here, and there is the insulation. It's a blown-in insulation in this type. It's not cellulose insulation in this, which would ease the process, because cellulose can keep a little bit more of water. It's blown-in mineral wool. So the conditions here are really hard. Yeah? So yeah, let's look. Have a look. This is during the construction, some photographies. This is the blowing in of the insulation. There's another remark to be made here. It's very difficult to control this. Yeah, you have to stand on the side, yeah, to control it, or you have to have some guarantee that it will be filled in any place. So this is something, yeah, in a lot of old buildings we have to do it this way, but recommend there has to be quality assurance in these situations. This is the airtight membrane we used in this construction. We thought that there might be a problem with the little holes we get by the nailing of it, but it's so tiny it wouldn't be important, but we kept some caution here. That was the very first time we did it. This is how the airtight connection was made to the plaster. I'll show that in more detail later on. This part of the membrane will be covered by the plaster. That's the way it has been done. Yeah, this is the covering of the membrane by the plaster. So now let's have a look on these measurements. What you see here is relative humidities. Again, relative humidities. This is a measure for how far apart from condensation risks we are in this construction. And what you see, these are the internal relative humidities. They are in the range between 30 and 50% during winter in this ventilated building. So that's, I think, completely okay, so no problem with that. And then we see, of course, that the relative humidity in the construction will be higher when we go to the outside. Now, this is completely normal. Because just the temperature drops, and with the drop of the temperature, the capacity of the air to hold the water is less, so the relative humidity will be higher. And of course, also on the outside, we have outside air with a humidity of around 90 to 95%. Yeah, so that is normal. What shouldn't happen, it should not go up to levels above these 90%. Yeah, and that's what we see here. So we have the measurement on the external, on the internal side of the external sheeting, and that's around some 90% here, and that's the corresponding simulation. And that's all still fine. We are still in a range where this is also normal. Even in a ventilated roof, you won't be lower because that's what you normally have on the outside. You have this average of about 90%. So yes, it looks like it's working. No more than 91% of relative humidity, and this is corresponding to about 14% mass percentage of humidity in the timber material, which is okay for timber material. Yeah, you could go up to 17, 18 without any problem. Yeah, so that's demonstrating, yes, this can work in the circumstances we already discussed, that it's airtight, really airtight from the inside, and the water vapor diffusion is somehow controlled. And we also did some simulations how it would vary if we vary the material used for the inside vapor retarder. Yeah, so that is the vapor retarder we actually used, the blue one. This would be a adaptive retarder that would reduce it. It doesn't look very much, but it gives you some more safety. It wouldn't help you if it's not tight. It's also clear. It has to be airtight. Yeah, can you prove it? Also, you can have similar effects with using materials for the insulation, which can store a little bit more of condensed water, like the cellulose. It's a similar effect. It will be a little bit lower than this. Yeah. So that is showing also from a scientific point of view that these types of construction, they can work if done properly. But you also see, of course, that the vapor content here is always increasing, and it stabilizes at the end at that level of about 13 to 14%. So there's a complete match between what we are calculating. This is done with a simulation, program Delphine it's called, between the results we get from this simulation and we get from the measurement. I have already shown you. Yeah? These are the measurement results, and those are the simulation results. And that's the, according to the standard, that is the limit. Yeah? So we are significantly away from that limit. But what I've shown you here, most important thing in order to be able to do that is to have it built really airtight. So now some hints about how that can be done in such a type of construction. If you have this combined timber roof construction and the wall plaster as an airtight layer, I've already shown that. Yeah? So that would be the air retarder, vapor retarder on the inside, and then there will be this reinforcement covering the film. And the plaster put upon the film, so the film is completely embedded in the plaster. And that's what you see here. Now it takes a little bit longer for the plaster to dry out, because it cannot dry out in this case to the external side. Yeah? So that is how it has been done. And this is what we already were able to show after 25 years. It's still tight after 25 years. So there's no question about that. It's something that should work. This is one of the important things. There are different kinds of measures. I won't talk about that because that's too long time to take. There's different kinds of measures how you can do this connection between the roof and the wall construction in such a situation. Paul has shown another one using this expansion. There are lots of other ways also to do it, but that's not what we are talking about here. We just have checked here whether it's really tight. This is a measurement been done with theater fork after about 25 years, and you see there is no driven movement of that fork. And what you also see here is, of course, there is a crack in the. So it's not. It wouldn't work without this airtight layer. Yeah? It's not enough to just have a plaster connecting the wall to the roof. It will never work because there's almost movement between the roof and the wall. Yeah? You cannot avoid that movement. Yeah? So there has to be a layer which is capable to keep being airtight with this movement. And that's one solution I showed, another one Paul has shown. Yeah? So yes, we have solutions to that. This gives you also some ideas how such types of problems can be solved. That is how to have a airtight connection in a masonry construction to a window. Now there is often a misconception here, that is that you try to connect the masonry wall to the window. Yeah? This is how people think about it. Now we have to see that a masonry wall is not airtight. Yeah? So the masonry itself, it's not airtight. So it doesn't make any sense to connect something which is not airtight in an airtight way to the window. What is airtight in a masonry wall is the plaster, the internal plaster. So this is a way of thinking here. So as soon as you have realized this, it's easy to solve it. What we have to connect is the airtight layer of the plaster with the frame. And that's the way you can do. This was done in this project was done by caulking. Now we have other materials nowadays which you can use here even easier, but we checked that. This is from the construction side. Yeah, that was a plaster end rail. The plaster connects here. There is a layer, a separation layer between the plaster, the masonry construction and the elastic joint material. That's also very important. That's the reason why some people say elastic joints won't work because they always will rip. No, they will work. The reason why they rip is if you do not have the separator here. Yeah, because then it will also be fixed to the wall, and the space it has to bend is too small, so then it will rip. So that is an important part of that kind of connection. Very easy to do if you know how to do it. It's also not new. It's well known in the building industry for a long time, but it somehow got forgotten, yeah? and that's the reason why it's in many cases being done the wrong way. Okay, so this is a photography after 25 years. This is how it looks now. And I told you it looks like this. I removed the wallpaper Make some photography, you see that is the acrylate layer, this is the window frame, this is the plaster, this is the end rail. It's still tight, and we checked it also. We measured it before and after. So I'm not going through this now, I have been signalized, I'm already a little bit out of time. We can do really airtight building envelopes. We have proven that now for several decades. There's a lot of measurements being done, especially in passive houses. Yes. Some people say, here that's maybe cheating. They have exactly 0.6. No, it's completely okay. Sometimes you do a measurements and you start the measurement with a higher value, like Paul has shown you. And then you improve and you do it as long as necessary, and that is the 0.6, or maybe your aim is even lower. Now, there is no reason, I won't talk about that, but I will just tell you, there's no reason to go even lower than say 0.1, or so there's some kind of extra sports we can do the most airtight building. I just have seen in Britain they managed to have 0.02 or something like that. I have to be honest, I think that's nonsense, yeah, because you don't need it to be that tight, and I just open the window once and close it, not completely in a proper way, and you will add to that 0.1, 0.01, another 0.05 or something like that. So it doesn't make any sense to go much beyond that. Okay, there's also another reason I don't talk about that. So this is the airtightness measurements after 25 years of occupation. And what you see in the range of accuracy of these measurements, they have also a range of accuracy. You have a little bit wind going, you have installed the blower door in different ways, you cannot always do it in the windows have been closed in a different way. You can correct it to some amount, but there are differences in the results. And these differences in results are shown with this accuracy bars. And you see all the measurements here are almost all within the measurement accuracy. So it's a range of 0.2, 1.25 air changes per hour. An interesting thing with that very first building, because we didn't know about any of these things when we built these buildings. We only knew that it's important to make it airtight, and we were surprised ourselves. Our goal was at that time, maybe we can achieve at least a bit better than 1 air changes per hour. We were surprised that at the very first measurement, was the very first measurement done here, we already achieved 0.24, because we were very cautious in all of these details. Yeah, some other results from that research after 25 years. That's a thermographic view from the outside of the western wall. What you see here again is no thermal bridges. Yeah? If it's free of thermal bridges 25 years ago, why should it be? There be thermal bridges after 25 years, as there are no. Yeah? We also did measurements on air quality. It's an interesting thing. We already realized the air quality in the first years where we did the measurement. Indoor air pollutants, we measure a lot of different kinds of indoor air pollution, like VOC, cyclic hydrocarbons, and so on. And we realized that most of those did not come from the construction, they did come from the furniture and from other things which were used in the building. And now it's interesting that changed after the years. So this is a successful path we have gone in German society. Nowadays, furniture, well, old furniture doesn't emit very much, but also the new ones we bring in, we are now almost free of these kinds of emissions. So interesting to see. The only thing which was increased is the terpenes. That's also interesting, because a lot of producers, they substituted the old solvents by the natural, so-called natural. I'm skeptical about that, and also all my colleagues who research on that. It's not clear that this is better than for human health, yeah, to have a natural solvent. It's always better to avoid that completely. Okay, some measurements of built passive houses. Already said, it's important to do these measurements. These are on the right-hand side. There's no depressed zero here. This is 0, 50, 100, and so on. These are measurements in existing buildings. What I told you is not only the differences in weather conditions, but also differences between different users. it's clear. Yeah, there's an older couple were maybe using a wheelchair, sitting in the building all the time, no physical activity, so they might need a little bit higher temperature. When the young guys are outside most time and doing lots of sports activities, so you have these differences. And it's very difficult to avoid these differences. Yeah? You can try to do some education on the persons, yes, you can. There's some influence of that, but lots of these differences are due to just health facts. Yeah? It's not so easy to change that. So now we go to the low energy building we have seen in the very first introduction. Yeah? And you still have these differences, but on a lower level. Yeah? There's a difference between the existing buildings and the low energy building of savings of at least more than 50%. Now we go to the passive house developments. This is what you see on the right-hand side. Now you see, you still have these differences between the different users. We have to be aware of that. That is what definitely will happen. You have users with higher consumption, you have users with lower consumption. The only thing what matters for the environment is the average consumption. Now, to be honest, I don't care about these guys with the higher consumptions here. They are still extraordinarily low, low enough for sustainable development. It's not the case here, but here we can be a little bit relaxed about that. What is important is the average. And what is also important, of course, that's an important message for the designers, especially also the designers for the heating systems and cooling systems, and also the investors. You have to be aware of this situation, that there might be some users who act differently. And it might be very difficult to convince all of them to change their behavior. This is what we know. Yeah? So we recommend to design a building in a way that the building will still work properly also with these different kind of users. Yeah, so that it will be positive in the reaction to the user. So we can deal with a part of the users, say 5% of the users, which have a significantly higher consumption. It's not a big deal. There are others which have a lower consumption, and the only thing which matters is the average. Yeah? But we cannot deal with complaints. So if there are users who complain that it's not warm enough or it's getting too hot during summer, that's not a good idea. Yeah? So that is why the passive house has to be designed in a way that it will also work for those users which are not using it in a proper way. The only thing what will happen, of course, we can't avoid that, these guys will have a higher consumption. Yes, they will. It's very difficult to avoid that. Okay. It's in average a 90% reduction. Some examples from buildings in China, also have already shown that it's spreading now almost everywhere. That's one of the big developments. Well, Paul also was there, you have seen that, so they are building like crazy right now. You see those high-rise buildings coming up in China at almost every place where you can build, and sadly, most of them are not energy efficient buildings, are not passive houses. Well, these ones are. This is a big development which has been done in China. And it's also interesting to see that the authorities are aware of the problems we are running into. So they are really concerned about it. They really want to do something about it. They are still not completely convinced that the way of energy efficient construction is the best way to do it. But we are looking forward to the results. There's also measurement being done in these buildings that at the end they will realize that that's in fact the easiest way to go. There are also discussion, nuclear fusion and other options. Of course, that is how politicians think. And so I'm convinced that this type of solution is the best solution we can do, because it's not only reducing the amount of energy we need, but it's also improving the internal living conditions, the indoor air quality, and the comfort in the buildings. Okay, so my last slide, call for papers for the International Passive House Conference. What I have seen here in the last few days is, for me, it's a good, there are good examples being realized in this region. and would be worth to present some of those also at the next international conference. So thank you so much for your attention.
Bueno, muchas gracias a todos por la atención. Espero que haya merecido la pena, no tengo ninguna duda. Tenemos un cafecito y unas pastas para acompañar a este momento. Y una cosita, hay un grupo de gente que saldrá rápidamente.